Today we look at a very important section in electronics, single stage transistor amplifier. We know basically a transistor is used for amplification purposes. Weak signal has to be amplified. So we look at a single stage transistor amplifier in common emitter mode, which is most commonly used one, the common emitter mode. So here is the amplifier. The amplifier has biasing. Biasing is provided by R1 and R2, and we have the resistances RC and RE. RE is the emitter resistance. RC is the collector resistance. So here various circuit elements are there. R1, R2, RC, RE, resistances are there. Then we have the capacitances, Cin, input capacitor, Cc, the coupling capacitor, Ce, the emitter bypass capacitor. Also, we see various currents passing through the circuit. We have this I1 and passing through R1, and the current passing through R2 is also I1, because the base current is very, very weak or very, very small in value. So we can assume that the same current I1 passing through R1 is passing through R2. We have the base current IB, sum of capital IB and small IB. Similarly, IC, sum of ICs, small IC. Then emitter current, sum of IE, small IE, like that. So these currents are passing, and we will be explaining how we get these currents like this. Let's find the circuit elements and their functions. R1, R2 and RE form the biasing and stabilization circuit. R1, R2 and RE. We know R1 and R2 form the circuit elements for the voltage divider bias. Okay, R1 and R2 form the voltage divider bias. Also the RE that gives the stabilization. Okay, that gives the stabilization. And so these are the components, R1, R2 and RE. R1 and R2 form the biasing, and RE give the stabilization. And we have already explained how RE is providing the stabilization. Then Cin, the input capacitor is there. Cin, the capacitor shown here. This is used to couple the signal source to the base of the transistor. Okay. If it is not used, the signal source resistance will come across R2 and thus change the bias. Okay. Signal source resistance will come across R2 and it will thus change the bias. In this, capacitor Cin allows only the AC signal to flow and isolates the signal source from resistance R2. Otherwise, as I said here, the signal source resistance, the signal source, that will have a certain resistance, and that will come in parallel with the R2, and that will ultimately change the biasing conditions. Okay, and also we know a capacitor blocks DC and allows the passage of AC. So the capacitor Cin allows only AC signal to flow, but isolates the signal source from R2. emitter bypass capacitor C. The emitter bypass capacitor is used in parallel with RE to provide a low reactance path to the amplified AC signal. Okay. So we are using RE across, CE across RE. This is RE. This will be providing a low reactance path to AC. AC can very easily pass through the CE. So AC, only DC current will be passing through this RE. Okay, AC current finds a low reactance path. Okay. So if the CE is not used, then the amplified AC signal flowing through RE, that will cause a voltage drop across it, thereby reducing the output voltage. So if you are not using CE, the amplified AC signal will be flowing through RE. Okay, DC already flows through RE, but if CE is not used, the AC, amplified AC current, that also will be passing through RE, and that will cause a voltage drop across it, thereby reducing the output voltage. It will reduce the output voltage. Okay. Now the coupling capacitor. The coupling capacitor is here. Coupling capacitor is here. It coupling capacitor couples one stage of amplification to the next stage. Okay, it couples one stage of amplification to the next stage. Okay, if we are using several stages of amplification, coupling one stage to the other, that is done by the coupling capacitor. Now suppose that we are not using it, then the biasing conditions of the next stage will be changed due to the shunting effect of RC, because that will come in parallel with the upper resistance R1 of the next stage. Okay. Okay. The next stage also has voltage divider bias circuit R1, R2. If we are not using the coupling capacitor, RC will come in parallel with that R1, and that will change the biasing conditions of the second stage, or the latter, the next stage. In short, the coupling capacitor isolates the DC of one stage from the next stage, but allowing the passage of AC signal. Okay, so coupling capacitor isolates the DC of one stage from the next stage, but allowing the passage of AC signal. Okay, so these are the functions of various components used in the amplifier circuit. Now what about the various currents? Various currents passing through the circuit. When no signal is applied in the base circuit, suppose that we are not applying any signal, only power supply is there, then DC base current IB flows through the circuit. Through the base, DC current will be flowing, and DC base current IB will be flowing through it. DC base current IB also flows when AC signal is applied. Now signal source is connected, the base current IB also flows through it. The total base current is given by, the total base current I capital B is given by IB plus small ib. So this is the total base current. The total collector current, when no signal is applied, this will be flowing. And when signal is applied, this current also will be flowing. And total collector current will be given by this. And this equation holds IC equal to beta IB. Similarly, small IC equal to beta small IB. The emitter current IE, okay, that is capital IE plus small IE. So I capital E, that is the DC emitter current when no signal is applied, and this one is the additional emitter current flowing when signal is applied, and this is the total emitter current. And this condition is satisfied. IE, that is equal to IB plus IC. IC, the base, the emitter current, that is given by this. Okay. So these are the various currents flowing through the transistor circuit. Now, a phase reversal, a kind of 180 phase difference between input signal applied and the amplified signal exists in the single stage common emitter transistor amplifier. Okay. So there is a phase difference of 180 degree between the signal voltage and output voltage in a transistor amplifier, common emitter amplifier. And this is the common phase, the phase reversal. Okay. So what that means is when input signal voltage increases in the positive sense, the output voltage increases in the negative direction, and vice versa. So when input signal voltage increases, the output voltage increases in the negative direction. And when signal input voltage decreases in the negative sense or increases in the negative sense, then the output voltage increases in the positive sense. Then we can clearly see here. See here when the input voltage increases, see the output voltage is decreasing. Similarly, when the input voltage is increasing in the negative sense, the output voltage is increasing in the positive sense. Okay. So we have this kind of phase reversal or 180 degree phase difference between the signal voltage and output voltage in a common emitter amplifier. And this is called phase reversal. The instantaneous output voltage across the collector emitter and the collector and emitter end of the power supply, that is this point here, the voltage difference between this point and this point. So that voltage appears across the load RL, or we can say the kind of AC voltage. Anyway, this voltage between the collector, this is the collector end, and the emitter end of the power supply. This is the emitter end of the power supply, the ground. This voltage, that is given by the total voltage here is VCC. From this point to this point it is VCC. Here the voltage drop is given by ICRC. So if we take VCC minus ICRC, we get this voltage drop. Okay. So that is given by VCE. VCE is equal to VCC minus ICRC. Okay, VCE, that is given by VCC minus IC RC. Now, if we take delta VCE, okay, delta VCE, the change in VCE, that will be equal to minus delta IC into RC. Okay, because VCC constant, the IC has this component, IC has capital IC plus small ic, and this IC is constant. So we have to take only the change in small ic. So delta VCE, that is equal to minus delta IC RC. Okay. So when signal voltage increases in the positive half cycle, the base current also increases, and when the base current increases, the collector current also increases. So as the collector current increases, the ICRC increases, ICRC increases. As ICRC increases, this voltage, the output voltage, the voltage between the collector end and the emitter end of the power supply, that decreases. So as the signal voltage increases, the base, the signal is applied to the base. So the base current increases. As base current increases, we know the collector current will increase. As the collector current increases, this will increase. As this increases, this is VCC minus this ICRC. So VCE will decrease. Okay. Similarly, as the signal current decreases, this will decrease. As this decreases, this kind this is happening in the negative direction. So this will, the VCE will increase. Okay, VCE, this will become positive. As IC, this becomes negative. So the VCE will increase. So this explains the phase reversal. Okay. So that is also given by this equation, delta VCE, that is equal to, dVCE, that is equal to minus dIC RC. So the main idea is there is a 180-degree phase difference between the input signal and the output signal, or the output. Now the DC and AC equivalent circuit. Actually, we can analyze our common emitter amplifier, the circuit, under DC conditions and AC conditions. DC conditions means you are not applying the signal. Okay, so only DC current flows. So we need to consider only DC current. Okay, so here it is assumed that in the DC equivalent circuit, it is assumed that no AC signal is applied, and we need to consider only DC voltages and current. So no AC signal, no signal is applied, and we need to consider only DC voltage and current. Since capacitor blocks DC, okay, so AC signal is not there. So capacitor, as you know, it blocks DC. All capacitors look like open circuits in the DC equivalent circuit. So all capacitors look like open circuits in the DC equivalent circuit. So to draw the DC circuit, we reduce all AC sources to zero. Signal is providing AC current, or it is the AC source, that is zero, and we open all the capacitors because DC cannot pass through capacitor. Okay, so this is the circuit that we get, and this is the circuit that we get, and this is called what? The DC equivalent circuit. Okay, this is called the DC equivalent circuit. Now applying Kirchhoff's voltage law to this, we have VCC equal to, VCC is the voltage appearing across the positive end of the power supply, and the ground. So that is sum of IC, voltage ICRC, VC plus IER. Okay. So we have this VCC equal to VCE plus IC into RC plus RE. Okay, VCC equal to VCE plus IC into RC plus RE. Okay. So VCE that is now given by VCC minus IC plus IC into RC plus RE. And when IC 0, okay, when we draw the load line, we take the maximum and minimum values of the collector current. When IC 0, we have the VC max that is given by VCC, and when VC is 0, this is 0, we have the IC max that is given by VCC by RC plus RE. Okay, so these are the maximum maximum values of the collector emitter voltage and collector current, and this will be helpful to us to draw the load line. Okay, so this is all about the DC equivalent circuit, and the next class we will be seeing the AC equivalent circuit.